Hi, so in this video we're going to look at how we resolve forces on a force diagram. So this diagram over here is what we're going to be eventually resolving forces on. We'll just have a quick recap of how to do it on a triangle. So here we've got a triangle, we've got our theta there. So we remember that sine theta is opposite over hypotenuse and cos theta is adjacent over hypotenuse, and both of these can be rearranged to be that actually the opposite is just the hypotenuse times sine theta, and the adjacent is the hypotenuse times cos theta. So given that, we've got this triangle, that's theta. This is our opposite side. This is our opposite side here. So if we call hypotenuse, let's call it F, which means this side here, this opposite side, is h sine theta, so it's just f sine theta. And this adjacent side is f cos theta, yeah? So look, yep, opposite is hypotenuse times sine theta. Our hypotenuse is a false, so it's called f. So the adjacent side is always f cos theta, and the opposite side is always f sine theta. And now if we rotate that, we're going to tilt this triangle. Okay, we're just going to tilt it to be this one, so actually this is now our theta. Right, and all we've done is tilt it. So this is our f, this is our f cos theta, and this is our f sin theta. Right, so this triangle is the important one. Okay, so let's see if we can select that. We're going to bring that over here. We're going to move all that over here. Don't need that for the moment. Great, so now we're going to look at this force diagram here. Right, so the first thing we need to do is draw a particle has weight. Well, let's read the question. The figure above shows a weight of 12 kilograms on a plane inclined at an angle 30 degrees. The box is in equilibrium. So equilibrium means that it's not moving. It has a light, inextensible string. Light means the string hasn't got any weight. Inextensible means it's not going to stretch, which means the tension is constant throughout every part of the string, which means the acceleration, if it was to move, it means the acceleration will be the same, but ours isn't going to move. We don't need to worry about that. The light bit's important. It means that the string doesn't weigh anything. In the vertical plane containing the line of greatest slope. Is the question being very specific, just that this string is parallel to this surface. It's not being moved at a different angle, which means all the tension is putting it up the slope. So the box is a particle. We're trying to find the tension. Tension in the string, which is called P, and a normal action in the box and the plane. So first of all, I need to draw some forces on my force diagram. So it's got the tension on there for me. So I need weight. Which I'm going to call mg, and I need a reaction force. The reaction force is always perpendicular to the surface. Right, so they're my three forces. I've got a string with a force P, I've got a reaction force R, and I have weight, which I've called mg. So that's the mass of the particle times the gravitational pull due to Earth. Right, actually they've given us the weight. So let's go back and change that. Where's the rubber? They've given us the weight, so we don't need to. If we didn't, because they've given us a weight, we can put it in there. We know the actual weight is going to be 12g. Right, now, if it's in equilibrium, it means that the forces are balanced, but they have to be going in opposite directions. So we can think of this force of the box, whilst it is going straight down to the Earth. If you think of a box on a plane, we know some of it is going to be going, some of the weight is going to be acting down the plane, and some of the weight is going to be acting into the plane to keep the box on the surface. Now we need to resolve this weight into these two components. So if this angle theta, if that's theta, see here where I'm putting the mouse, that would make a 90, that would make a right angle triangle, which means this one here is 90 minus theta, and this line here is perpendicular to the surface, which means this force here is a right angle. So if this is 90 minus theta, this bit here must be theta. Okay, so if that angle's theta, that angle's theta. Now we can sort of see we've got a line here, which is false, which is the same as on our triangle. And we've got a resolved bit here, which is going to match this bit here. So we can call the weight going into the surface F, it's the force, which in this case is 12G, times cos theta. And now we've got this other line here. But this other line here is parallel to this one here. On our triangle, because this here and this here, they're components of the force. Right, vectors can move around in space. They're allowed to move in space. So this F sine theta, if we draw a line here, this line is equivalent to that line. They're just in different places, but they've got the same value. So that line there would be F sine theta. So now we can see that. Now we can see this one here is the same as this one here. This one here is the same as this one here. And this last one here is going to be this bit here. So that becomes our force, which is 12G in this case, times sine theta. Right, and now because it's in equilibrium, it's not moving, which means the opposite forces are equal to each other. So we can just finish this off by saying, because it's in equilibrium, opposite forces equal each other, which means P must equal 12G sine theta, and R equals 12G cos theta. Let's do another really quick example. Oh. Right, so I'm just do it really quickly again, but I'm just going to change this weight to be M. Okay, so we've got the same issue. We're trying to resolve it. It's exactly the same question. We can put our weight in. This time we don't know the weight, but we can call it mg. We've still got r. So the first step is draw your forces. Second step is to resolve our forces. So we're going to resolve our weight this way. That angle's theta, which means this angle is always theta. We resolve into the surface, we get mg cos theta. We resolve down the slope, we get mg sine theta. And in 3, we write our equation so that it's in equilibrium, so the opposites are equal. So R equals mg cos theta, P equals mg sine theta. I just realised this question actually gave you the angle, yeah? It gave you 30 degrees. So that's fine now. We can just go stick 30 degrees in here and then use your calculator to work out the value of 12 times G times sine 30. and that'll be your final answer. Okay.